All right, this review is about work, energy, and power. Remember that work is a transfer of energy, so that when you do that, you change joules from one type of energy to another. The equation to calculate the work being done is force times the displacement times the cosine of the angle in between them. If the angle is 0 or the force is the same direction of the displacement, that is when the most work is done. And at 90 degrees, there's no work done. In a case something like this where the displacement is the right, if the force is down, no work would be done because it's 90 degrees between them. The net work done, which is if you add up all the work from all the forces, results in a change in kinetic energy. Remember, our kinetic energy equation is 1/2 mv squared. Also, for potential energy, remember that comes from work being done against a conservative force. Remember, a conservative force is a force that if you go too far, it's going to help you go back. And the conservative forces that we use are gravity and spring. If you lift something too high, gravity will pull it back down. For gravity, the potential energy is mass times gravity times height. And for elastic with a spring, it's 1/2 times k times x squared, where k is the spring constant measured in newtons per meter, and x is the squish or stretch, which is measured in meters. Conservation of mechanical energy. Remember that mechanical energy is the kinetic energy plus the potential energy. And there's conservation as long as there are no non-conservative forces. Something like friction or air resistance would make this not applicable. To solve these problems, we start with ME1 equals ME2. We might have someone snowboarding down a hill, and they would start with gravitational potential energy and end with kinetic energy. So we have mgh equals 1/2 mv squared. We could have elastic potential energy. We would need to think about that. Or we could also have non-conservative, and remember that we need to put that in there, and that would be what energy is lost to heat or sound. We also talked about power in this unit. Remember, power is how quickly work is being done, or work divided by time. Work itself, time doesn't matter. If you do a specific job, it doesn't matter how quickly you get it done. You would do the same work as someone else that did it slower, but you would have more power because you would have done it in less time. We could also alternatively find power by doing work over time, and remember that work is FD cosine theta. And assuming that your force is in the same direction of the displacement, that cosine theta is 1, and we have FD over t. Well, distance over time is velocity, so you could also get power times force times velocity. Remember, work is a change in energy, which is measured in joules, and time is measured in seconds, and power is measured in watts. If you're using power equals FV, you would have to use a free body diagram, and the sum of forces equals MA to find the value of the force driving the car or a person. So let's look at an example. If we have a force that's 30 newtons at a 60-degree angle pushing on a box, and we push the box for 20 meters, we could calculate how much work is done by using FD cosine theta, and we'd find out that it was 300 joules. But what if we want to know what's the velocity at the end? Well, we could use the work energy theorem. Work equals a change in kinetic energy, which is kinetic energy final minus initial, and if it started at rest, we could go through the algebra and determine that the final velocity would have been just over 12 meters per second. Let's look at a conservation of energy problem. We could start with a cart that's moving 10 meters per second at the top of an 8-meter hill, and there's a spring with a spring constant of 20 newtons per meter down at the bottom of the hill. We want to know how far is the spring going to squish. Well, we would start with ME1 equals ME2 because mechanical energy is conserved. We need to determine what types of energy, so we think, is there velocity, height, or squish? Well, at the top we have velocity and height, but no squish. So we have velocity, 1/2 mv squared, and height gives us gravitational potential energy, mgh. Then at the bottom we think the same thing. Is there velocity, height, or squish? Well, there's no velocity or height, but there is a squish, so we use elastic potential energy, 1/2 kx squared. Then we can put the numbers in, and we can actually just do some algebra and solve for x. And in this case, we find out that X is about 6.8 meters that the spring's going to squish.